we're getting back together, like ever.
Are you okay? Are
Wait.
you sick or something?
No.
Oh my god.
Oh my god. I don't know what's going on lately. It's getting really hard to breathe.
Wanna know why? It's because of the air pollutants. Sulfur monoxide, carbon dioxide, nitrogen dioxide, and benzene. But to get it better, let's get to the lab. Let's go! Wait! I forgot about the solid contaminants, which are asbestos, black carbon, cadmium, and chromium. Let's go!
Guys, you finally arrived! Take a seat. I got everything ready. Let's get going! Here we have the Lewis structures for a diverse variety of contaminants. But what does this all mean? Molecular geometries come in these three different types. Angular, which has angles, tetrahedral, which forms a tetrahedron, and linear. It's just a line. It's boring. We can also see here which molecules belong in each type. Nitrogen dioxide and sulfur dioxide are angular. All the ones with carbon, the chlorine methane and the methane, are both tetrahedral, and the linear is carbon dioxide. And here we have another extrapolation, which is the electron geometry. All that are angular have trigonal electron geometry. All that are linear have linear electron geometry. And all the tetrahedral have tetrahedral electron geometry. Right? Follow me! Oh great! You arrived! Anyways, I was about to talk about...
We might, but if voice change, right? Anyways, I was about to talk about acid rain. The weather forecast said it would rain today. What does this mean when there's contaminants on the air? So we have SO2 and NO2, which react with water. They create H2SO3 and H2CO3. H2SO3 is a non-polar molecule with London dispersion forces and a tetrahedral geometry. H2CO3 is a trigonal planar geometry, and the H bonds is polar. And all this, what it was with rain, is they turn rain into acid by decreasing the pH to below 5.6. Back to normal. So, now that we have talked about acid rain as one of the effects of contamination, let's talk about some other types of contaminants. Here we have liquid contaminants. These are HNO3 or nitric acid and H2SO4 or sulfuric acid. Here we see that this one has a boiling point of 87 degrees Celsius, is polar, and has a viscosity of 0.76 centipoise at 20 degrees Celsius. This one has a boiling point of 337 degrees Celsius, is also polar, and has a viscosity of 27.7 centipoise at 20 degrees Celsius. We can see that this one's clearly harder to get rid of, as well, it has much higher viscosity, and also it has much higher boiling point. Here, some other type of contaminants are the solid contaminants. Let's talk about their characteristics. Carbon, when finding its allotropical carbon, is usually tightly packed and amorphous, but it can also be found as an allotropical diamonds and graphite. Graphite is what is in your pencil, and both of those are crystalline. Cadmium depends on what it's compounded with. For example, if it's compounded with sulfur, which makes it a sulfide, it has cubic crystal structure. And also we have asbestos. Asbestos has a crystallite with a sheet-like structure. And chromium has a body central crystal structure. But anyways, what is your solution to all of these pollutants? Activated carbon. But why is activated carbon so good? Well, let's talk about it. This guy is mostly made of H and C, which is hydrogen and carbon. It is also non-polar and only has dispersion forces. But it's also a great absorbent, as it's a porous substance. And with this porous substance, we can place it in filters in contaminated areas, which take in the contaminated substance and give it out without contamination. This has actually already been done with air filters and water filters that actually use activated carbon. Again, we can use it because it's very porous. And for this to actually work as a solution, we need international cooperation. Is there any precedent for this? Yes, there is. Of course there is. These two treaties, the LRTAP and the Stockholm Convention on POP,